Integration by parts. Let's start with the product rule from Calculus 1. We know that the derivative with respect to x of the function f of x times the function g of x is f of x times the derivative of g of x plus g of x times the derivative of f of x. Now, because each of these are functions in their own right, we can take the antiderivative of both sides of the equation here. So we have the integral of the left-hand side with respect to x is equal to the integral of the right-hand side with respect to x. Now, on the left-hand side, when you take the antiderivative of the derivative, the fundamental theorem of calculus tells us that those cancel out. And on the left-hand side, we just get the function f of x times g of x. And on the right-hand side, we can do these integrals separately. So we have the integral of f of x times g prime of x times dx plus the integral of g of x times f prime of x times dx. And then what I'm going to do here is solve for this one. So when I do that, we get the integral of f of x g prime of x dx is equal to f of x g of x minus the integral of g of x times f prime of x dx. And this formula that you see here is the integration by parts formula. And it is one of the most important techniques of integration that we have. What it basically does is it allows us to find antiderivatives of products of certain kinds of functions. So here is that formula in a much cleaner format. Now, I want to show you another way to look at this formula. Let's suppose I let u be equal to f of x, and I let v be equal to g of x. Then we know that du would be f prime of x times dx, and dv would be g prime of x times dx. And if you make a comparison to this formula here, I want you to see that f of x is u, g prime of x times dx is dv. Again, f of x here is u, g of x is v, and then g of x here is v, and f prime of x times dx is du. So another way to think about this formula is the integral of u times dv is equal to u times v minus the integral of v times du. And you can see that I'm getting this from these substitutions up above here. And this is the more useful format of integration by parts. Let's take a look at an example. Suppose we want to find the integral of x times sine of x times dx. What I need to do here is view the product as a product of some function u and the derivative of some function dv. Now, there will be guidelines for how you choose which one is which, but for right now, let's just assume that u is equal to x, and sine of x times dx would be equal to dv. Okay, so now if you're wondering what exactly I'm doing here, I am trying to make a comparison to the formula u times dv. So part of this I need to let be equal to u, and the other part I need to let be equal to dv. Now, how do you know if it's going to work or not? Well, a lot of times you don't until you do it. So let's go ahead and go through it and see what happens. So if u is equal to x, then du would just be 1 dx. And if dv is equal to sine of x dx, what would v be equal to? So here you have to be a little bit more careful, because when you go from u to du, you're just taking the derivative. But when you go from dv to v, you have to take the antiderivative of this function. And the antiderivative of sine is negative cosine. So let's plug in what we know. We have the integral of x sine of x dx. Again, this is my choice for u. This here is my choice for dv. So according to the formula, that should be equal to u times v, which is this function times this function, so x times negative cosine of x, minus the integral of v times du. And v times du is the product of these two things, right? V and du. And when I multiply those, I get negative cosine of x times dx. And this is definitely an improvement, because the reason we couldn't do this integral in the beginning is because we had the product of an algebraic function and this trigonometric function. And we know how to take the antiderivative of each one of these separately, but we don't know how to take the antiderivative of the product of these two. Now we know it improved because look at the integral that you have over here. This integral is just the integral of cosine, which we know how to do. So this is a definite improvement. All right, let's go ahead and simplify here. X times negative cosine of x is negative x cosine of x. The minus and the minus here becomes a plus. And then we have the integral of cosine. Now let's go ahead and do it here. We have negative x cosine of x plus the antiderivative of cosine is sine. And that is it. We do plus c, and we have the antiderivative of x times sine of x. And keep in mind, you can always check your answer by simply taking the derivative of your answer and showing that it's equal to the function that you started with. And I'll do this here just this one time. If I take the derivative of negative x cosine of x plus sine of x, here we are going to apply the product rule of derivatives. So we take the first function, negative x, multiply it by the derivative of cosine of x, plus, then we're going to take the derivative of the function negative x and multiply it by cosine of x, plus, and then we have to take the derivative of sine. Let's go ahead and do the math here. We have negative x times the derivative of cosine is negative sine of x, plus the derivative of negative x is negative 1 times cosine of x, plus the derivative of sine is cosine. Negative 1 times cosine and positive cosine cancel out. And we end up getting negative x times negative sine of x, which is x sine of x. And I'll just point out that that was the original function that we started with up here. So again, the method of integration by parts is for taking antiderivatives of products of functions. Now our second example is really simple. We want to evaluate the integral of the natural log of x. And let me just caution you here real quick. I see this all the time, right? And this, of course, is not true. Remember, it is the derivative of natural log, which is 1 over x, not the antiderivative. So you have to be really careful not to confuse derivatives and antiderivatives. Okay, so how should we do this function? Well, believe it or not, we need integration by parts here. So let's go ahead and bring in the formula. So what we have to do in our original problem here is we have to decide what is u going to be equal to and what is dv going to be equal to, because that's how the integration by parts formula begins. Now, we don't have a lot of choices for u. All we have here is natural log of x. So I'm going to let u equal that. And then dv will simply be dx. Let's try this and see if it works. If u equals natural log, then du is going to be 1 over x times dx. And if dv is 1 dx, then v is just going to be x. Now, according to the formula then, the integral of natural log of x dx is going to be u times v. So we are multiplying these two together. So that gives us x times the natural log of x minus, and then we have to do v times du. And that's the product of these two things. And that's in an integral. So we have integral of v times du. So it's x times 1 over x dx. And this is very doable because x times 1 over x cancels out the x's, and we end up getting, for that integral there, just the integral of dx. And the integral of dx, of course, is just x. And so the antiderivative of the natural log of x is x natural log of x minus x. When using integration by parts, the fundamental choice you have to make is what to let u be equal to. Once you've decided that, then dv will simply be the remainder of whatever was in your original integration problem. So here we have a way to make recommendations on your choices for what to let u be equal to. And it's the acronym LIATE, which sometimes people pronounce LIATE. L stands for logarithmic functions. So if you have a logarithmic function in your integral, it is your top priority for what to let u be equal to. The next highest priority is inverse trig functions. Next is algebraic functions. Algebraic functions include radicals, rational functions, polynomials, etc. T stands for trigonometric functions, such as sine, cosine, and tangent. And lastly is E, which stands for exponential functions. So this will provide you with some guidelines for what to let u be equal to. Please understand that these are only guidelines and it is not always going to produce a successful outcome. Let's take a look at an example. So here we have the integral of t squared times e to the t. So we need to identify that t squared is what we would call an algebraic function, and e to the t is an exponential function. So out of algebraic functions and exponential functions, algebraic functions has a higher priority. So when we go to set up our integration by parts for the integral of t squared times e to the t dt, I'm going to let u be equal to the algebraic function t squared first. Now, once I've made that choice, once I've chosen u to be this, then dv is going to be the rest. And so dv would have to be e to the t times dt. Now we just calculate du, which is 2t dt, and then v is the antiderivative of e to the t, which is e to the t. Now, integration by parts tells us that this is going to be equal to u times v, so that is going to be t squared times e to the t, minus the integral of v times du, which is 2t e to the t dt. Okay, now the next step is, can we do this integral directly? And the answer here is no, because once again, we have integration by parts needed here. We have an algebraic function multiplied by an exponential function once again. So we need to repeat the process of integration by parts for this integral now. And before I move on, we need to talk about what do you do with the number 2? Well, it turns out it doesn't really matter. You can leave it as part of the integral or you can factor it out, but you have to decide what you're going to do there. Personally, I like to factor these things out since it keeps our choices for u and dv a little bit simpler. So I'm going to rewrite this as t squared e to the t minus 2 times the integral of t e to the t dt. Now I'm just focused on calculating this integral, which will be a new integration by parts problem. And for that one, we once again have an algebraic function multiplied by an exponential function. So I'm going to let u equal t. dv will be e to the t times dt. Now du is just 1 times dt, and v is once again e to the t. So again, keep in mind, when you calculate du, you're taking the derivative of this. And when you calculate v, you're taking the antiderivative of this. Okay, now we apply integration by parts again. Let's keep everything that we had, t squared e to the t minus 2 times. Now, what is this integral? Well, integration by parts tells us it is u times v, which is going to be t e to the t, minus the integral of v times du, which is e to the t dt. And now you can see that we no longer need integration by parts because we know how to take the antiderivative of e to the t. That's a basic formula. So we have t squared e to the t minus 2 times the quantity t e to the t minus the antiderivative of e to the t is e to the t, and then plus c. And finally, we'll just clean this up a little bit. T squared e to the t minus 2t e to the t plus 2 times e to the t plus c. And all I'm doing here is distributing the negative 2. You could leave your answer like this, or you can factor out e to the t, which would give you t squared minus 2t plus 2 plus c. Now, both of these answers are acceptable, but it's pretty typical for answers to be factored in the end. In our next example, we have the antiderivative of e to the x times sine of x. Let's go ahead and remember our priorities in terms of what to let u be equal to. So in this problem, we have an exponential function here, and we have a trigonometric function here. And we can see on our list that trigonometric functions have a slightly higher priority than exponential functions. So I'm going to start here by letting u be equal to sine of x. And then dv will be whatever's left, which is e to the x times dx. From there, du will be cosine of x dx. And v, of course, is just e to the x. And so we have the integral of e to the x sine of x dx is equal to u times v, which is e to the x times sine of x, minus the integral of v times du, which is e to the x cosine of x dx. Now, if you look at this integral here, you can see that it is the same type of integral that we started with. So we're going to have to use integration by parts again here. Now again, we have a trigonometric function and an exponential function. So I'm going to start by letting u equal the trigonometric function, and dv will be the exponential function. Du, of course, will be negative sine of x dx, and v will be e to the x. Now, it's very important you keep track of your parentheses here. So we have integral e to the x sine of x dx is equal to e to the x sine of x minus the quantity. And then here we're going to do u times v, which is e to the x cosine of x, minus the integral of v times du, which is e to the x times negative sine of x dx. Now, let's just pause for a minute because the integral we end up with here, if you look at it carefully, it's a lot like the integral that we started with. So we get what is called a repetition here. Let's remove the parentheses and see what we have. So integral e to the x sine of x dx is equal to e to the x sine of x minus e to the x cosine of x. And then this negative gets distributed to this negative, turning it into a positive, but then we have another negative on the outside. So this is going to be minus e to the x sine of x dx. And this is called a repetition because this integral here is exactly the same as the integral that you started with. So if you do another integration by parts, you'll just go into an infinite loop of continuing to try to do integration by parts. So instead, what we do here is we recognize this as a quantity. So I have minus that quantity. I'm going to add that quantity to both sides of the equation. Now, why am I doing this? Well, because these will cancel out. That's the primary reason. And then more importantly, on the other side, if we have one of these integrals plus another one of these integrals, we get two of those integrals. And so now look, to solve for the integral of e to the x sine of x dx, all we have to do is multiply the left side by 1/2 and multiply the right side by 1/2. And what happens is that cancels out the constant here, and we get the integral of e to the x sine of x dx is equal to 1/2 e to the x sine of x minus 1/2 e to the x cosine of x plus c. And again, on your final answer here, you could factor out the 1/2, and you could also factor out the e to the x and write the answer slightly differently. So in our next example, we have a definite integral. We have the integral from 0 to 1 of inverse tangent of x. Please be very careful once again. I will tell you that I see students do this kind of mistake all the time, right? This is, of course, not true. What is true is that the derivative of inverse tangent is 1 over 1 plus x squared. Okay, but this is the antiderivative of inverse tangent. So we can't do any of this. All right, what should we do? Well, in our antiderivative here, we only have one function. We have inverse tangent of x. That's the I part of Lie8. So we should let u be equal to inverse tangent of x. We really don't have a choice. And then dv will be whatever's left, which in this case is just dx. And then du now is the derivative of inverse tangent. And v is the antiderivative of 1 dx, which of course is just x. And so the integral of inverse tangent of x dx is u times v, so that is x inverse tangent of x, minus the integral of v times du. And when you multiply those together, you get x over 1 plus x squared dx. Now, I want you to notice that I am keeping the limits of integration out of the problem. In this case, you want to do your limits at the very end. So the next step is I just want to focus on doing this integral now. And this is a simple integral. This is just a basic u substitution. Okay, so not integration by parts, just basic u substitution. If I let u be equal to 1 plus x squared, du will be 2x dx. And the integral of x over 1 plus x squared dx, all I have to do now is put a 2 there, put a 1/2 on the outside, and this integral becomes 1/2 integral du over u, and that is going to be 1/2 times the natural log of the absolute value of u, which is 1/2 times the natural log of the absolute value of 1 plus x squared. So here is the work for that integral. Now let's just bring in the solution. So we have x inverse tangent of x minus this antiderivative is right here. So that's 1/2 natural log absolute value 1 plus x squared. And now that I have my antiderivative, I will just take this whole thing and put in my limits now from 0 to 1. So what's important is that you're not changing your limits. Even though we did a u substitution, don't change your limits because This part has to use the original limits. So you want this part to use the original limits as well. All right, so now we just need to plug in. So when you plug in 1, you get 1 times inverse tangent of 1 minus 1/2 natural log of 1 plus 1 squared. Minus, when you plug in 0, you get 0 inverse tangent of 0 minus 1/2 natural log of 1, right? Because when you put 0 in here, you get natural log of 1. Natural log of 1 is 0. Inverse tangent of 0 is 0. And we end up getting 1 inverse tangent of 1. The inverse tangent of 1 is pi over 4. And then we have minus 1/2 natural log of 2. Now, why is the inverse tangent of 1 equal to pi over 4? Well, if you just draw a simple triangle, if you have an angle theta, you know that tangent is the opposite side divided by the adjacent side. And so if these are both 1, then you know that this angle must be 45 degrees or pi over 4. In our final example, we have the integral from 0 to 2 pi of the function t squared times the sine of 2t. So once again, we have a product of an algebraic function here and a trigonometric function here. Between algebraic and trigonometric, we should let u be equal to the algebraic function first. So I'm going to let u be equal to t squared. dv will be the sine of 2t dt. du, of course, is 2t dt. And v is the antiderivative of the sine of 2t. And that is negative 1/2 cosine of 2t. Now, how do you get that? Well, if you know your formulas, you can get it directly. If you don't know your formulas, then you have to do a separate little u substitution problem to figure out what this is. All right, so now integration by parts tells us that we're going to get u times v, so that will be negative 1/2 t squared cosine of 2t minus the integral of v times du, which is negative 1/2 times 2t times the cosine of 2t times dt. Now the 1/2 and the 2 cancel out there, and this becomes negative 1/2 t squared cosine of 2t minus is plus integral of t cosine 2t dt. So once again now, two things. I'm leaving off my limits because I'm going to get the complete antiderivative and then come back and plug in the limits. But the other thing is I have to do integration by parts one more time here. So for this one, I'm going to let u equal t. dv will be cosine of 2t dt. du, of course, is just dt. And v is the antiderivative of cosine of 2t, which is 1/2 sine of 2t. And again, that's a u substitution problem if you don't know the formula. So this now becomes negative 1/2 t squared cosine of 2t plus this integral is u times v. So that's 1/2 t sine of 2t minus the integral of 1/2 sine 2t times dt. So one final integral to do there. So this integral here is minus 1/2 times, and what is the antiderivative of sine of 2t? It is negative 1/2 cosine of 2t. So this all becomes negative 1/2 t squared cosine 2t plus 1/2 t sine 2t plus 1/4 cosine of 2t. So that's the antiderivative of your original function, but now we have to use the limits from 0 to 2 pi. So that's going to be our last step. Take this whole thing from 0 to 2 pi. Now, When you plug in 0, you have to be careful because a lot of times when you plug in 0, you get 0. And you do in fact get 0 here when you plug in 0 because t squared will be 0 when t is 0. You will get 0 here for the same reason, but you do not get 0 here because cosine of 0 is actually 1. So be careful. Don't just assume when you have 0 as a lower limit that you don't have to actually plug it in. So first, let's go ahead and plug in the upper limit 2 pi. That gives us negative 1/2 times 2 pi squared. Cosine of 2 times 2 pi is 4 pi, plus 1/2 times 2 pi times the sine of 4 pi, plus 1/4 times the cosine of 4 pi, minus, now what I just mentioned here, when you plug 0 in here, you're going to get 0. When you plug 0 in here, you're going to get 0. But when you plug 0 in here, you get 1/4 cosine of 0, and that is 1/4. So now let's finish it up. Cosine of 4 pi is equal to 1. Sine of 4 pi is equal to 0, so this goes away. And the cosine of 4 pi, again, here is equal to 1. So what we have here is negative 1/2 times 4 pi squared times 1 plus 1/4 times 1 minus 1/4. So here these cancel out, and we end up getting negative 1/2 times 4 pi squared, which is negative 2 pi squared. And that concludes this video lesson.